Okay, so today we're going to wrap up propellant combustion, which will segue nicely into multi-phase combustion. And so what we'll do for the rest of the course is starting on Friday, we'll have a really brief review of droplet combustion. Then on Monday, we will discuss particle combustion with application to coal and aluminum. Then we'll go into group effects, and then we'll go into how they're actually modeled. And then the last week will be some applications. We'll swing back and do some stuff with modeling RDX combustion, which involves some aspects of multi-phase combustion because there's bubble formation. Then we'll discuss a few other things. Okay, but the last couple topics for propellant combustion is we will just briefly discuss heterogeneous propellant combustion or composite propellant combustion. And recall that a composite propellant is not homogeneous, is that there is a binder, which is HTPB, that basically locks a bunch of oxidizer crystals in place, usually ammonium perchlorate, and also there can be some aluminum particles that are in the propellant as well. And so this binder HTPB is basically a rubbery compound that basically holds everything in place, and it acts as a pure fuel normally. There is research into making binders energetic too, which would sort of help things along for both propellants and explosives. And then you got the oxidizer crystals. And so whereas for the homogeneous propellant, we had a nice one-dimensional analog where we could model it, and it's sort of becoming almost mundane enough to where it becomes a viable class project, as you guys know. But a heterogeneous propellant is much more complicated. There's no true one-dimensional flame. It's at best quasi one-dimensional, meaning that you can average this and sort of make up something that is one-dimensional. But to predict how fast the flame burns and everything like that, you need to consider the structure of the propellant itself, where that was a non-issue for a homogeneous propellant because there was no structure. So for heterogeneous propellant, we need to consider all of this structure. And some of the most modern simulation techniques for this, and because of that, you often need to go to a computer to be able to solve these. And one of the most modern simulation techniques was developed by Tom Jackson while he was at the University of Illinois, Chicago. Right now he's here at UF and he works with Bala quite often. And he pioneered a technique that's based on level set methods. And so it's the same level set method that I talked about when we're doing detonation shock dynamics. It's the same level set method, a surface evolver that I wrote for you for Computer Project 1. Except for instead of marking a detonation surface, what Tom did was he developed it to mark the surface of all the different ingredients of the propellant. So there's a level set for the surface of the ammonium perchlorate. There's another level set for the surface of the aluminum particles. And then when you start to put everything together, you can actually sort of randomly, it's called a random pack. You can basically randomly pack all these different ingredients of a heterogeneous propellant, and you can place them inside of a binder, which is right here. And then he basically just starts the simulation and allows it to burn. Except for now, it's more complicated in the sense that he's dealing with ingredients where the chemical kinetics and all that stuff is not as well known as it is for homogeneous propellants. RDX and the double base propellant model and nitromethane are three of the only ones that we can really model in detail. Again, at ARL and places like that, there may be more information, but at least in the public, nitromethane, RDX, HMX, and the family of double base gun propellants are the only ones that can be modeled. And so what you see here, this here is an AP crystal, and that's burning in a self-deflagration mode. And so you see a nice little flame plume here. And then here is where a binder is sort of pyrolyzing. And the highest temperature region is right where the oxidizer from the AP crystal and, oops, I should make this blue, and the fuel from the pyrolyzed binder, which is a pure fuel, meet and form a flame zone. And so the structure of a heterogeneous propellant is very, very complicated. And so how Tom did this was he assumes a regression model. It's sort of based off of a Zenin pyrolysis type model, where basically the regression rate of the AP and the binder follow their own different, basically Zenin pyrolysis laws. They have their own prefactor. There's a prefactor for the AP, there's a prefactor for the binder, and an activation energy for the AP, and an activation energy for the binder, which is normally HTPB, again, which is just a standard rubbery compound. Okay, so if we just look at this area here and draw a picture, here we have the surface of an AP crystal that is receding at some burning rate RB. We have the surface of the binder, which is a pure fuel, that is receding down at some burning rate of the binder. And then coming off of the burner or of the binder surface are binder pyrolysis products, which are very fuel-rich species. And then coming off of the AP surface, you have oxidizer-rich ammonium perchlorate pyrolysis species. And ammonium perchlorate is a monopropellant. And if the chemical kinetics for that were well known, you could model that in the same way that you do for any other homogeneous propellant. But unfortunately, at least to my knowledge, the chemical kinetics for ammonium perchlorate are not super well known. So what Tom did to get around this is he assumes two global gas phase reactions. So the first reaction is AP combustion. Okay, and so basically the AP will burn by itself. So he assumes that there are AP pyrolysis products X that come off of the surface, and then those self-react to produce AP combustion products Z. Okay, and so basically near the surface, it's pure AP pyrolysis products, and away from the surface, or and farther away from the surface, the ammonium perchlorate is going to basically self-deflagrate to produce very high temperature and oxidizer-rich gases. Okay, so now that takes care of this. Now on this side over here, we have very fuel-rich, high temperature or very fuel-rich pyrolysis products from the binder that are basically going up. And those can react with the final combustion products of the ammonium perchlorate, Z. So basically, he has another gas phase chemical reaction mechanism for the binder pyrolysis products, Y, plus the AP combustion products going to the final combustion products. And basically, he has basically net Arrhenius laws for these that have been sort of calibrated. And he has to do this because just the chemical kinetics is not super well known for these types of things. So if we were to sort of draw what the flame structure would look like, you would see there would be a fizz layer above the AP. Again, he's at a very high pressure, so the fizz layer is really, really, really thin. So it looks like it's sitting right, so it looks like the flame is sitting right on the surface, but in reality, it is shifted away from the surface just a little bit. And then you'll see a monopropellant flame. And so we'll have X coming off and Z basically auto-igniting to produce Z through a luminous AP flame. Then leaving the surface of the binder, we have the binder pyrolysis products Y, which are fuel rich. So we have a fuel rich region here and an oxidizer rich region here, and these two are allowed to burn. And where they basically mix, they burn to form a sort of non-premix style diffusion flame of basically AP pyrolysis product or AP products and the binder products. Okay, so again, the flame structure, and so you see a lot of these little diffusion flamelets. It can be an inverse flame depending on the relative size of the gaps between the AP crystals. So the structure gets really complicated, and so but in reality, all this is occurring at the same time on all these little AP crystal surfaces and the binder pyrolysis surfaces. So this stuff gets sort of very, very complex. And so in this picture here, you could almost consider this little line here being the initial reaction zone for the AP pyrolysis combustion products. This region here is where it is rich in Z, are the AP combustion products. And we have the binder pyrolysis products here, and then they basically meet and then burn in a non-premix style of combustion, where the burning between the binder pyrolysis products and the ammonium perchlorate combustion products is basically limited by how fast they can mix. Okay, and so even though the burning of a heterogeneous propellant is much more complex, they still tend to follow Saint Robert's law. That's AP to the N style burning. They still follow that. They are still subject to erosive burning. They're still subject to dynamic burning, and they're still subject to flame spreading. So all of the stuff that I discussed for homogeneous propellants is still in play, but erosive burning and dynamic burning become a bit more complicated, because you could imagine, if you're looking at this surface here, if you have a very high speed cross flow, it is also possible for shear forces to dislodge AP crystals and basically rip them off the surface and convect them into the flow. And so there's also, not only is there thermal and sort of chemical reaction based erosion, but if you have a heterogeneous propellant, there's also mechanical erosion that you need to worry about too. Even if you don't have particles impinging on the surface, you have shear forces that, if there's a strong cross flow, that are trying to rip out all the AP crystals and things like that. So, heterogeneous propellants are much more complicated, and you need to go to really advanced 3D simulations. I know this technique was made by Tom, I think on the order of 15, 20 years ago, and he's moved on to actually doing packs of actual AP crystal shapes, and then basically the size distribution of the AP crystals that are actually used in the propellant affect its burning rate. And so because of all these different ingredients that are mixed together, and the size distribution of those particles makes a difference, modeling and designing a heterogeneous propellant is much more complex. And also heterogeneous propellants tend to be used for rockets because you don't really care too much about these particles. But for gun propellants, those tend to use homogeneous propellants because you don't have all these sort of solid particles embedded in the propellant, which for a gun barrel, you do not want solid aluminum oxide particles flowing at high speed down the barrel. They will erode it as they move by it just due to friction, and also they'll sort of stick onto the surface, and then they'll act as an abrasive when the next sort of round moves through the barrel, and so it really affects barrel life. And so gun propellants tend to be homogeneous, and rocket propellants tend to be heterogeneous, where those effects aren't that big of an issue. Because
Professor.
Yeah.
What's the reason for having all the different size crystals? Like, why are some like a lot bigger than others? Like, why they're not all the same size?
I'm sure initially it was just due to that's how they came from the manufacturer, and then they just mixed them in. But they find that the actual size distribution, if you have an AP crystal size distribution, and I don't know the specifics on this, Tom would be a very good person to ask if he can tell it. But I know that if the size distribution of the AP crystals is something like this versus something like this, you'll have two different burning rates of the propellant. So it just happens that due to the size of the sort of diffusion flamelets that form around all of the AP crystals, that basically affects how close the final combustion products are, basically how close that is to the surface, which affects the heat transfer to the surface, which affects how fast it burns. And so the size distribution plays a big role, and that's sort of one of the, even though for most heterogeneous propellants, we know the ingredients are usually HTPB and AP with some aluminum and maybe a few other little things, like catalysts which is rust, or iron oxide particles, things like that to sort of catalyze and control the burning rate. It's the size distribution and the exact mixtures and the exact mixture fractions of them used that are sort of kept under sort of lock and key. Yeah, even the one used for the space shuttle solid rocket booster, even though that one was designed about over 40 years ago now, well over 40 years ago, that propellant formulation is still under ITAR restrictions. So even though it's that old, just because back in the day it took a long time to develop these because it was just trial and error. These sort of fancy simulation techniques just didn't exist back then. And I know Tom and his consulting firm get a lot of work basically simulating these packs. And now all this erosive burning and stuff, to my knowledge, no one has done a simulation of a propellant under a crossflow. If Tom has been doing that, he's done it in the past year or two, just because that adds a multidimensional effect. And these simulations are very expensive and very big, even in this sort of quasi 1D mode. If you're going to get a convective burning or not convective burning, an erosive burning type of effect, you're going to need to make the computational domain very wide, which is going to make it much more expensive. But at any rate, despite all these complexities, for a lot of these propellants, you can find basically parameters for Saint Robert's law, and all of the effects that I discussed are also present, but they are complicated by just the fact that you have a mixture of different ingredients inside of the propellant. So are there any questions on this stuff?
Professor, kind of a question on the simulations. How long are the simulations for heterogeneous mixture compared to a homogeneous? Is it much more complex, or is it about the same?
If you want to realistically simulate a heterogeneous propellant, you have to do a big 3D calculation. You need to resolve all these little surfaces. And for a homogeneous propellant, and this here is about as 1D as you can get. For a homogeneous propellant, you can do a true one-dimensional simulation. And so 1D versus 3D is a huge difference in computational effort. And so that's also why, because of that dimensional simplicity, you start to see people simulating erosive burning and things like that with homogeneous propellants, or they'll do one-dimensional simulations with, say, 400 chemical reactions. Because they're known for homogeneous propellants, are known well enough. And also you're just doing the simulations in 1D, so it's practical to do that. Okay, but in general, because the flame structure for a heterogeneous propellant is not truly one-dimensional, they are much more expensive. They require big clusters, and I've never asked Tom how long the simulations take. It'd be interesting to ask him. But I know they're not cheap, and I know he uses the DoD or DOE machines, depending on who's funding his work on this. And by those machines, I mean, I don't know, on the order of a few thousand processors, I'm guessing, is what this would take, if not more.
Oh, wow.
Yeah, no, these These are not laptop style computations because of 3D. Yeah, the nitromethane stuff and the double base stuff, those are laptop style, sort of computations. You can do a whole suite of them. It'll take your computer, maybe 4 or 5 hours. But to do that to do a similar sweep for heterogeneous propellant would be somebody's PhD thesis, more or less, in terms of time and effort. Okay. Any other questions? Okay. One issue that I'm going to discuss is cracks, because that's a big issue for heterogeneous propellants. Because I don't know if you guys have seen an old tire that's just sitting around for years and years and years. But if you have, you may have noticed that it gets sort of quote unquote dried out and it forms cracks on it. Well, the tire is basically a rubbery compound, and the binder of a heterogeneous propellant is a rubbery compound. And if it sits there in storage for decades and ages, the same thing happens. It quote dries out. It doesn't really dry out, but that's just, a colloquial way of calling it. It basically self-oxidizes a sort of tiny bit, and it has the appearance of becoming drier. But then cracks will form in the surface. So a big problem if you have a rocket system that's sort of sitting around for a long time, and if you have the unfortunate event where you need to push the go baby go button and basically light it up, you need to understand how these cracks, which can form in the propellant surface, can affect how it burns. And so if the pressure for your rocket system is low, they're not going to matter very much. These cracks are very thin. This is a very exaggerated view of them. And also at low pressure, the flame standoff distance, which you can sort of view as the distance between the propellant surface and the gas phase flame of the propellant, or a mean gas phase flame if it's a heterogeneous propellant, it's simply too thick. Is that basically the flame needs, the gases need basically this much distance to burn from the surface, and this distance here, well, maybe not the way I drew it, but at low pressure, this distance here is larger than this distance here, so the flame cannot fit inside of the crack. But what happens at high pressure? Well, at high pressure, the rate of chemical reactions increases, and this flame standoff distance decreases, and it starts to move closer and closer and closer to the surface. So now what happens at high pressure is the flame standoff distance is significantly reduced, and now all of a sudden the flame can now fit inside of the crack. And like I said, at really high pressures, especially for like a tactical missile, where the rocket chamber pressures are higher, for the solid rocket boosters, the chamber pressure was, I believe, 650 psia, so not super high, just because they're dealing with a very big system, and they're trying to basically do heavy launch capabilities, meaning that they couldn't jack the pressure up to get to increase the thrust, because then you need to consider making the housing of the rocket strong enough to take that pressure, and then now you lose. If you make it strong enough, now all of a sudden they can't do the heavy lift capabilities. But other rocket systems don't have those concerns, or at least not nearly as much, and so they'll burn at a higher pressure. And so at higher pressures, the flame is now very thin, and it can fit inside of the crack. And so from the point of view of the flame, where the standoff distance can be on the order of a micrometer or even less sometimes, this flame is now free to propagate inside of the crack. And so now the flame, if it burns steadily, will see the crack as just a increase of surface area. Okay, and so the flame standoff distance XF decreases as the pressure increases. So at high pressures, this flame, as I said, fits inside of this crack. And just for your reference, this flame standoff distance, at least for a homogeneous propellant, is often proportional to pressure raised to some power. It's a different exponent than the burning rate, and it's dependent on the propellant, et cetera, et cetera. But just basically, this shows that this distance here decreases, to the minus m, I should say, p to the minus m, is it decreases with increasing pressure. Okay. Then if the flame is sort of small enough to fit inside of the crack, it will propagate inside of the crack. Now what happens if all of a sudden you have a pressure where the flame can't go into the crack because it's too thick, then it suddenly reaches a condition to where the flame can propagate into the crack. What it will look like is the flame will basically see a sudden increase in the burning surface area. And so now in your rocket, you not only have this entire surface area here, basically generating gas mass, you have the sides of the crack too that are also generating gas mass. So there is a net increase in the burning mass flux. If you increase the burning mass flux of the propellant, due to the increased surface area of the crack, you're going to increase the dynamically increase the rate of pressurization of the rocket. Okay, and so you can see that even if the crack remains intact, you're still going to have very undesirable effects for your rocket because it was designed for a nice smooth surface, not a surface that has all these extra little cracks. And so it's going to be operating at a very off-design pressure, which if you consider the structural loading and things that will encompass, that is very undesirable for them. But also, there's some really interesting dynamics that occur inside of the crack itself. So if we just sort of draw a control volume and look in detail at sort of one crack, if you were to just do a steady conservation of mass balance, you would realize that it doesn't take a very deep crack for, a steady mass balance requires that m dot in equals m dot out. You would realize that it doesn't take a very long crack to form before you realize that basically due to the very small exit area of the crack and the very large side area of the propellant that is producing gases, is that it's very easy for the flow leaving the crack to become choked. You know that this is sort of a constant or a variable area duct. So this would be a bit like a gas dynamic nozzle where you have mass injection. That's one of the classic configurations. You might learn that in gas dynamics, maybe not. Certainly not introduction to comp flow, but in gas dynamics you might. But anyways, even with this mass injection here, is that you cannot spontaneously, especially with the diverging area, you cannot spontaneously accelerate a flow beyond a supersonic condition, and so that same rule still applies. And so basically, the flow here is at most at the sonic at the speed of sound with respect to the propellant gases, and just due to how long these cracks are, that's not a very hard a condition to achieve. So now, basically, what does that mean? Is that, well, if you were to do a steady mass flow balance, that doesn't really care about this choke flow condition. Is that mass in has to equal mass out. And so if something happens, and so remember m dot equals rho a v, and if this is fixed at the sound speed of the propellant gases, and this is fixed by geometry, and if something, that means our only variable to change is the density of the gases. So if something happens and we increase the amount of mass going in, the only choice to increase the mass going out, because basically this is fixed this is fixed at a maximum of the sound speed. This is fixed by the geometry. Is our only choice is to increase the density. And what's the only way we can increase the density is if we increase the pressure. So basically, what happens if the flow becomes choked at the crack is basically to accommodate all the mass that is coming in, the pressure at the tip of the crack in the bottom will be far higher than the pressure of the gas exiting the crack. Okay, and that's basically just due to the choking effect. Is that you can almost think of this as this crack is acting like its own little rocket nozzle, in a way. So, and so basically, in the combustion chamber of this little crack-based rocket nozzle is the crack itself. Okay, and so the pressure at the head end of the crack will be much higher than the pressure at the exit of the crack. And so now what this can now, I think some of you can probably see what's going to happen here. If you have a very high pressure here and not so high pressure here, what's going to happen is this can cause the crack to grow. And so what happens then under the worst conditions is this crack grows and splits and it forms more cracks. And now all of a sudden, we don't just have this crack area here, we have all these side cracks too, and the burning area goes way up. And then now we haven't increased the exit geometry very much. And so we have all this mass now that basically needs to go out. And our only choice again is to increase the gas phase density, which again requires an increase of pressure. So in other words, if we reach if the crack reaches a significant length to where the crack starts to grow, it will self-pressurize due to this choking effect, and the cracks will grow. And they increase the surface area, which increases the rate of self-pressurization in the crack, which leads to more cracking, and then eventually it leads to a explosion of exploding of your rocket, which is obviously not desirable. And this cracking phenomenon has caused many rocket failures. And as I said earlier, it is a concern for propellants, like in the nuclear missiles. These things have been sitting around for 50 years. It's a very open question as to how that propellant behaves. I'm sure that's been studied, but that is a very under restriction. But this is a concern for any system where propellants are stored for a very long time, or the sort of manufacturing processes aren't very good for them, and are prone to leaving surface defects and cracks and things like that. Okay, so yeah, and I already went over this. So are there any questions as to the concepts of crack propagation and burning of salt propellants in cracks? Again, in reality, this is a very complex phenomenon. It involves gas dynamics, it involves a propellant combustion, and it can involve multi-phase flow if it's a heterogeneous propellant, and it also involves a coupling to solid mechanics. And so this is a very multi-physicsy problem. And to my knowledge, nobody has really solved, maybe at some of the DOE labs they have, but I doubt it. Their focus is more on the explosive side of things. To my knowledge, nobody has basically simulated all this stuff put together. Yes?
Just a quick question. You mentioned that the flame had to be thin enough to fit inside the crack in order to do this propagation into the crack. That wasn't just the fizz zone then, it's the fizz zone plus the first flame that needs to be.
They say the flame, it's probably gonna be, it's not a binary like 0-1 type thing. I would assume you'll start seeing these effects as soon as the fizz zone is small enough to get inside of the crack. And it will become progressively worse as more and more of the flame structure can fit inside. But that effect is not well known. It has not been studied very much. There certainly have not been simulations done basically of that, just because the propellant combustion world has been empirical for the past, almost completely empirical for about the past 20 years. Very difficult to get funding in this area. And something like that would require either an extremely clever experiment or a detailed numerical simulation. Does that answer your question?
Yes, it does. Thanks. Sounds like a fun project.
Yeah, it would be. So, and then the last thing I'm going to get into before we start to transition to multi-phase combustion is something that involves multi-phase combustion of propellant grains. And that's, we can consider the effect of confinement. And so say we have a closed volume and we have a chunk of solid propellant and we basically just light up the propellant. Well, the solid propellant will recede at some velocity RB. It will produce high pressure combustion gases that will then basically pressurize the chamber. And then as the pressure goes up, the burning rate goes up, and it produces a sort of runaway effect that can cause the chamber to explode, or even in the worst case, the propellant to detonate. Just note that an explosion is defined as a rapid release of pressure, basically where you deposit energy into a system faster than it can be basically naturally dissipated away, either due to heat conduction, a thermal radiation, or acoustic wave propagation. And a detonation is a sort of chemical reaction driven phenomenon. And so an explosion and detonation are two different things. So please don't mix them up. A detonation is an explosion, but an explosion is not necessarily a detonation. For example, if you pop a birthday balloon, you would certainly not call that a detonation, but that is an explosion, albeit a very weak one. Okay, and so this could explode due to the case rupturing, or in the worst case, if the case is strong enough, you could actually transition the propellant itself into a full-blown detonation. Now, no one really does this type of experiment. I mean, I don't know why you would, but there is a similar thing in the area of gun propellants. And so if you consider a closed volume, and that could be closed because you have a bullet or some sort of cannon round or howitzer round or something like that, that's at the end. And then what they have there is they have a bunch of little propellant grains that are in a fixed bed, or I mean, not a fixed bed, in a fluidized bed where the particle grains can flow and move and basically do their thing. And so if we were to treat this as a closed volume and ignite it from the end, basically what you would see is a completely different dynamic than you do for a piece of solid propellant, where it's just one large propellant grain. And for these gun systems, these could be grains of, say, JA2 or whatever modern double base propellant is used in the big guns. So what happens now is, with this system here, the products can only flow into this free area here. They cannot penetrate inside of the propellant just because it's a solid surface. But what if the surface is porous because it's just a bunch of loose powder? Well, the combustion products can, of course, go into this free area here, but some of them will actually basically propagate inside of the granular propellant bed, and then basically cause a really interesting effect. And so if I was to look at this and plot the temperature of the propellant, or the temperature of the gases and the propellant inside here, what I would find is that in this free space here, they'd be at some flame temperature. Then basically due to convective heat transfer, as these high temperature propellant gases basically pass between all the propellant grains, what then will happen is there will be convective heat transfer, and that will raise the temperature of the propellant grains. And so if I was to draw the same profile for the other case, what that would look like is something a bit like this. is that there would be almost no preheating effect. And so what this sort of convective heat transfer does is it produces a very broad, in-depth preheating zone of these propellant grains. And this is occurring only because the propellant gases can basically flow between the grains. I know I drew them like cylinders, but in reality, they would be spheres. And so even if they're touching, there's still a small gap where those propellant gases can basically flow between and basically heat everything up. And so, and then similarly, if I draw the pressure, what you'll see is a peak pressure in that free space, and then a decrease to basically some other pressure in this. And this pressure drop here, as the gas flows between the grains, is caused by drag forces. For those of you who've studied porous flow, that is called that's a phenomena called Darcy flow. Is that our granular propellant bed is definitely dense enough that to the gas phase it just looks like flow through a porous media. And then also you can look at the combustion products, is that the mass fraction of the combustion products will also penetrate inside. And so if you were to, if say the initial gas between all of the propellant grains was air, the front between the air and the combustion products would basically move basically with the combustion products as they penetrate further and further into the propellant bed. And so once you start adding those particle effects, this picture starts becoming very complicated. And you know, I was just drew a crude picture of it, and basically there's a more complete picture of it from done by Brazil while Steve's son was still at Los Alamos. We have a porous bed here. Over here you have basically burning particles over here. You have a thin region here where heat conduction is important, and you have a thicker region where basically the high temperature combustion products are basically penetrating and heating all the stuff in the porous bed. And then an actual burning front of the flame, and also a multi-phase combustion zone, because these particles will shrink. And then in this region here, you have a traditional burning dust cloud of propellant grains. And the reason that they are interested in this in Los Alamos is that high explosives are actually slightly porous, albeit a little bit, and they are concerned about studying this process for deflagration to detonation transition for a propellant, if there's an unwanted fire or something like that. And so they study this for safety reasons. But the same phenomena occurs unwantedly in gun systems. And so you have all these sort of effects going on. And so you could consider this, that if this was not a porous bed, the sort of permeation thickness or the convective preheat zone would be basically of zero thickness, and the thermal diffusion thickness would basically dominate. And so such a flame, when heat conduction is dominating the heat transfer into the propellant surface or a flame surface in general, it's called a conductive flame. If it's dominated by this convective heat transfer effect, it's called a convective flame or convective burning. And again, they're not even drawing all of it. Is that due to the burning at the surface here, some of the particles get ejected, and then you have big chunks of burning stuff that sort of come off of the surface of the porous bed. And then basically that's called deconsolidation burning. That also adds quite a bit. And so this phenomena of convective burning becomes very, very complex and very situation specific. And so what we'll do when we start to cover multi-phase combustion is to describe the equations that you could use to basically simulate a convective burning. But obviously, I can't give you any homework problems on that, just because that would be a PhD thesis, basically type of work. But what happens then, due to this, what's called convective burning, is that both pressure and temperature increase for the propellant grains, basically near the gas particle bed interface. As the temperature increases inside of the bed, that means the particles that are slightly inside of the particle bed can ignite and then basically start to burn. Then after they start to burn, if they're salt propellant, the burning of the salt propellant grains follows St. Robert's law. So AP to the end, they still burn like that. And so with this convective burning, not only do you have burning on the surface of the propellant bed, but due to the convective heat transfer, there's also in-depth burning too. Okay, and then basically this, and also the increased pressure at the surface increases the burning rate of the propellant grains. So this implies that due to this convective burning effect, there is a much larger surface area of the burning for the burning propellant than there is. It was just a perfectly smooth, flat surface. And so, and then if you do experiments, this burning front has been observed basically due to this in-depth burning and the enormous surface area and the convective preheating effect. This burning front can actually propagate at speeds of up to 500 to 2,000 meters per second. It can be supersonic, but it's not a detonation. It has not reached that state yet. But these produce very fast supersonic flames. They are normally disastrous if you encounter convective burning. It is normally something to be avoided at all costs, just due to how fast they go and how destructive basically they can be. Okay, and so this phenomena is called convective burning. It's also extremely dynamic. If you had a burning propellant and you wanted to model it, when we studied dynamic burning, it would definitely be in the truly unsteady burning regime, because the dP/dt would be extremely high. And the flow would be extremely fast. Everything about it would be sort of off the charts with it. And then also dynamics of motion dynamics of the propellant bed become important. You could imagine that if you have a bed of propellant here and basically high pressure gas flow that is basically pushing on the surface, it will actually compact the outer edge of the propellant and then basically decrease the sort of porosity. This decreased porosity makes it more difficult for the gas to basically penetrate in. And then also, it will also produce a phenomenon called compaction waves, where basically it's a front of colliding particles that sort of gather up. And so basically these are multi-phase flow effects that also affect the dynamics of this convective burning. So this stuff gets basically very, very complicated. And it also has been observed to occur in very narrow gaps. These were experiments done at Los Alamos, where they had, you can't see it in this awful picture here, but there was an 80 micrometer gap between two slabs of PBX 9501, which is basically HMX. And they ignited it from the closed end over here, and they basically watched how the flame propagated through. And so this here, apparently there's a flame tip right here. But anyway, so even though the gap is extremely small, they still see a very fast luminous flame propagating through it. They see extremely high pressures, depending on where they put the pressure transducer. They see pressures on the order of 800 megapascals. Again, it's nowhere near the 30-40 GPa that you would see for a detonation, but still high enough where they blew up a couple of their test rigs. And if you look here on their plot of the sort of flame speed, it's on the order in some cases between 1,000 and then 2,000 meters per second. And so these things propagate very fast. They're very dangerous, and they can even propagate in extremely small cracks. So don't, for this type of thing, don't expect sort of quenching effects to sort of save it. is that due to the high pressure and how thin propellant flames get at high pressures, these convective burning effects can also occur in cracks. And also, what's driving the phenomenon is convective heat transfer between, if you consider the two burning slabs, you have a slab here and a slab here, it's closed over here, is you have the burning surface over here, and the flow has no choice but to turn and then basically go downstream. And so even if this is the section of propellant here that is burning, you have high temperature combustion products flowing over the surface of the propellant here, and it is heating it up. And so there is a convective burning. So there is a convective heat transfer effect there that is also going on. And then also, as time goes on, there's enough burning area to where you form a shock wave that can propagate, and then that can also introduce convective heat transfer effects. And just, I'll ask one last question with this. So this convective burning stuff, if this propellant bed here, if I change the particles to, say, coal or carbon or fuel droplets, would you expect this convective burning effect to be important or not? The answer is no. The reason for coal or fuel droplets is that even if they're in a porous granular bed, is that the fuel droplets or coal particles or what have you are pure fuels, and so they need an oxidizer to burn, and that oxidizer is the surrounding air. But what's going on here is the gas that is heating them up is high temperature combustion products. So basically, as the high temperature combustion products were to flow through that bed, is it would push the air away, and the gas surrounding all of those coal particles or aluminum particles or basically whatnot is not air, but it is combustion products. And so unless those particles can burn in the combustion products, even though they're at a high temperature, they are not free to burn because there's no oxidizer for them to burn. And so this effect occurs mainly with propellants because they carry their own oxidizer. And then it does not matter if the gas surrounding them is air. They'd probably burn a little bit better if it was air. But it does not matter to them very much if it's air or if it's high temperature combustion products, because they carry their own oxidizer. But if this was a bed of basically coal particles, you do not see these convective enhancement effects. And in fact, the flame would basically normally quench just because you'd have so much heat loss to the surface, and there'd be no subsurface burning, and so it would just die out. So are there any questions with this?
I got a question. How do we know that this effect is dominated by convective heat transfer instead of an increase in pressure in that area?
Well, because you have to ignite the. You mean, are you talking about the slabs or the granular bed?
I was just thinking of this as like a gun cartridge, and you ignite the back end. You're going to have a pressure increase from all that gas that's being released.
Yeah. Well, it's a 1-2 punch. Is first you need the high temperature gas to flow through and basically heat them up to the point where they ignite. But then after they ignite and then steadily burn, then the sort of pressure effect from St. Robert's law comes into play. But they have to ignite first. And salt propellants do not ignite via pressure.
Got it. Okay.
Right? So does that make sense?
Yeah, so you need the preheating in order to get them to a state that they're ready to auto-ignite. And then once they ignite, the pressure effect can take advantage of that.
Yes, exactly. Because again, for a flame, the primary mechanism that increases the temperature of the reactants to a point to where they can, to basically where they can, to where there is sustained chemical reaction, is for a traditional flame, it is heat conduction. Basically, there is heat conduction from the high temperature products transferring thermal energy to the cold reactants. And so basically that is what's heating them up. If you were to kill that and have no heat conduction, you have no flame. It just sits there and does nothing. And then, but in these multi-phase, multi-dimensional scenarios, you have additional effects that can transfer heat from the high temperature products to the cold reactants. And one of them is this convective heat transfer effect here. And that can occur in narrow gaps or in granular propellant grids, like in a gun cartridge. Or if in the gun cartridge, they design a porous propellant, because those grains have all sorts of little holes and channels drilled into them to produce this effect and basically decrease the flame spreading time. And then also you can have radiatively dominated flames. Those produce a different sort of signature. We're not going to get into those in this class. I think doing combustion and shock physics and multi-phase flow is enough things coupled in one problem. But for a propellant, is that in a deflagration mode of burning, there needs to be some sort of heat transfer to the cold reactants to basically heat them up. For a detonation, you don't have that effect because the shock is so strong that it's the shock compression alone that is heating up the reactants to a point to where they can rapidly burn. But unless it truly transitions to a detonation, this convective burning, that effect is not important for this convective burning. Even at, what temperature did Steveson have here? Or pressure? Yeah, even at, say 700, say at 0.7 GPa, that's nowhere near enough of a shock wave to produce those kinds of temperatures in the propellant where they start to basically, where the shock compression alone would be enough to raise the temperature of the reactants enough to rapidly burn. Does that answer your question?
Yes, it does. Thank you.
Yep. Okay, are there any other, stop sharing. Are there any other last minute questions?